In this presentation, I want to address a question that is rarely made explicit when we compare scientific theories. We usually compare models by how accurately they fit observations. But accuracy alone is not enough. What matters just as much is how the theory was constructed in the first place. Specifically, how far its foundational assumptions are from the phenomena it later claims to explain. This distance, which I will call epistemological or predictive distance, plays a crucial role in determining the explanatory value of a theory. The central question is not whether a theory matches the data, but how close the theory already was to that data at the moment it was built. This is not about numerical proximity or computational precision. It is about conceptual distance. How many assumptions were introduced before the phenomena appeared? How much of the answer was already encoded in the framework itself? These questions are rarely asked explicitly, but they are fundamental to understanding what a theory truly explains. A theory that starts close to the phenomena it explains has fewer ways to fail. Its success is therefore less surprising. In contrast, a theory that starts far from observation takes a much greater risk. It can fail in many ways. When such a theory nevertheless converges toward real phenomena, that convergence carries much more epistemic weight. The success is informative because it was not guaranteed. We can broadly distinguish two types of theories. Some are constructed specifically to address a known anomaly or dataset. Their architecture is shaped by the data from the beginning. Others are constructed from deeper principles that are not targeted at any particular observation. In those cases, the phenomena emerge as downstream consequences. Both approaches are valid, but they do not have the same explanatory meaning. Physics provides many examples of short-distance success. The Big Bang model was introduced to explain cosmic expansion, homogeneity, and isotropy. Inflation was later added to resolve additional observational tensions. Quarks were introduced to organize an exploding zoo of particles. Lambda CDM was assembled to fit expansion data, structure formation, and supernova observations. These models are extremely successful, but their core components were introduced because the data demanded them. Their success is therefore expected. General relativity begins with a geometric postulate: freely falling matter follows geodesics in a curved spacetime. The field equations are then constrained so that, in the weak field and slow motion limit, the theory reduces to Newtonian gravity and Keplerian orbits. This reduction is not accidental. It is explicitly enforced as a consistency requirement. As a result, planetary motion is very close to the theory's construction. This has an important consequence. Agreement with Newtonian gravity in the Solar System is not a high surprise prediction of general relativity. It is a boundary condition. The success of GR in weak field gravity is real and impressive, but epistemologically it lies at short distance from the phenomena it explains. The theory was designed to succeed there. The hypergeometrical universe starts from a completely different conceptual layer. It does not begin with spacetime geometry, curvature, geodesics, or classical gravitational forces. None of these concepts are assumed at the outset. Instead, WHO is constructed from microphysical principles that are initially disconnected from astronomical observations. The first principle is the fundamental dilator, a dynamic, shape-shifting deformation of space that propagates at the speed of light. It is not a metric chosen to fit trajectories, but a physical entity whose propagation and interference generate effective interactions. The second principle is the quantum Lagrangian principle, or QLP, which is imposed to prevent particles from dissipating simply by existing. It is a stability requirement at the quantum level, not a gravitational hypothesis. At no point in the construction of WHO is it required that Newton's inverse square law be recovered, that Keplerian orbits exist, or that classical gravitational phenomenology appear. These features are not imposed as boundary conditions or tuning requirements. The theory is allowed to fail completely at the classical level. Despite this, when the interaction law derived from the fundamental dilator and the QLP is written down, the Newtonian limit appears by simple inspection. It emerges as a limiting behavior of the force itself. It is not enforced, adjusted, or retrofitted. This emergence marks a fundamental epistemological difference between WHO and theories that are constrained to reproduce known results. Because WHO begins so far from observation, its agreement with known physics is not guaranteed. It could have produced no inverse square behavior, no closed orbits, no stable two-body motion, or wildly incorrect secular effects. The space of failure is enormous. This is what gives its eventual convergence significance. From the same interaction law, WHO recovers Newtonian dynamics as a limiting case, predicts perihelion precession without invoking spacetime curvature, handles genuine two-body systems, and reproduces binary pulsar orbital decay through dynamical quadrupole radiation. WHO challenges Mond by deriving from first principle the minimum acceleration in this universe. A simple analytical derivation. Mond can only postulate its existence. WHO delivers WHO Patti Salam Su, 4, gut model to replace quantum chromodynamics and repositions quantum electrodynamics in the 4D spatial manifold, eliminating nonsensical considerations like antiparticles travel backward in time. WHO also solves the twin paradox, and explained both de Broglie waves and the double-slit experiment. It also explained quantum eraser experiments, quantum entanglement. These results are not patched together from separate assumptions. They come from a single underlying framework. The same framework also explains galaxy rotation curves, derives a minimum acceleration scale from first principles, accounts for large-scale attractors, the great attractor, produces the 3D map of the universe, and addresses early galaxy formation. These results are not postulates added to fixed discrepancies. They are consequences of the same microphysical assumptions. When discrepancies arise between theory and observation, there are two possible responses. One can force the new theory to conform to the old framework, or one can ask whether the old framework is a special or limiting case of the new one. This choice is methodological, not philosophical, and it strongly affects interpretation. Empirically, the asymmetry is clear. Forcing WHO to adopt the effective assumptions of general relativity breaks correct predictions. In contrast, correcting GR by adopting WHO's two-body mapping or eccentricity dependence resolves residuals without damaging GRE's established successes, including binary pulsars. This pattern emerges from the data itself. Standard weak field expressions in GR effectively treat precession as a property of a test particle in a central field. In genuine two-body systems, especially with non-negligible eccentricity, this identification becomes ambiguous. Who adopts a different mapping between what is measured and what is modeled, and that mapping is empirically successful. Scientific progress is not only about improving fits. It is also about reducing assumptions. A model can fit the data perfectly and still explain very little if the structure was already built into it. Explanatory power depends on how much was assumed before the fit occurred. Short-distance theories are excellent at describing the world. Long-distance theories aim to explain why the world looks the way it does. This distinction does not determine truth, but it does determine explanatory depth. Final thought. The wager behind who. Science advances not only by adding parameters, but by reducing assumptions. A theory that starts close to observation can describe reality. A theory that starts far away, at the level of particle stability and space deformation, and still converges toward observation may explain why reality has the structure we observe. That is the wager behind the hypergeometrical universe.